And here we are again, fluid dynamics, this time pathlines. Now we start with deriving an equation of motion for a single particle, because in fluid dynamics we're always dealing with some kind of fictitious element, volume element, collection of particles, packet, whatever you want to call it, like wave packets, particles, elements. Anyway, and then we shrink those volume elements down, so to get them into a differential form, which is easy to deal with rather than a continuum. But now I'm going off on a tangent. So we start by deriving an equation of motion for a single particle. Let's say a stone is thrown through the air. Then by Newton's law we get ma, mass multiplied by acceleration, is this, which is F equals ma. Now we know that our weight is equal to our negative mg and j, which is acting downwards, our gravitational force is acting downwards, which gives rise to our negative part here, and j is obviously the component, vector component ijk, and j representing the the unit vector component in the y direction, in this case negative y, which comes out of the wash as negative mgj. Now neglecting air resistance, and as always neglecting air resistance, what I meant to say, and as always m cancels, which in Newton's law obviously you can just divide both sides by m and you'll get this here. So the second derivative with respect to time equals minus gj. Now we have r here, which is our xi plus yj, which is a standard generic form with our unit vectors I and j in x and y. Now say initial height is non-zero, and at some height, so we have r of 0 equal hj. Now dr of dt of that 0 point equals this, where v sub 0 cosine theta of 0 I plus v sub 0 sine theta of 0j. So we integrate our second derivative with respect to time, which gave us this form, our minus gj, and substitute the second initial condition, which will give us this equation here, which this should start looking quite familiar for our dynamic equations if you've done any kind of classical mechanics dynamics. Now we're integrating and substituting first initial condition, which gives us this, where x equals v of 0 cosine theta of 0t, and likewise y equals minus 1/2 gt squared, which should be very familiar to should be just very familiar, plus v naught sine theta naught t plus h. Now t provides a natural parameter for our path of the stone. Now natural parameter of the shape of the path is followed by eliminating t between these two equations, which gives us this, and pictorially it will look something like this. Somebody here lobs a stone, it goes and takes this path, and which is this equation here. Now here's an example. Well, that was to give us the basic idea. This was a dynamic equation of like projectile, yeah, that's the right word, isn't it? Yeah, projectile motion. So we're going on to a more fluidy type of situation now, and this is an example of finding an equation of path lines for a fluid flow with velocity u equals ayi plus btj, where a and b are specific constants. We will sketch path lines for a fluid particle which passes through points x and x naught, passes through the point x naught at t, for x equals -1, 0, 1, 2, 3, and so on. Now using equation dr by dt equals u which gives this equation. Now, since by definition dr by dt equals our velocity components in the y and x and y direction, we have dv by dt equals a of y and dy by dt equals bt. Now, second equation, y equals 1/2 bt squared plus c, where c is an arbitrary integration constant. Then from the first equation we obtain this: dx by dt equals ay equals 1/2 abt squared plus ac. Now, integrating, we get this: x equals 1/6 abt cubed plus act plus d, where these are constants. Now, pathlines passing through point x0 at t equals 0 must be such that x equals our given x. Now, y equals 0 and t equals 0, y of 0 equals c equals 0, and x of 0 equals d equals x. So the pathlines equations are here: x equals 1/6 abt squared plus x, and y equals 1/2 bt squared. So x minus our given x equals 2a squared over 9b y cubed, and this is the equation of our pathline with solutions here, where x equals -1. We started from x equals -1. We're going up here r1, r2, r3, r5, and so on, approximately like this, as we're going on for the values of x that we're given here. Right, now yeah, now that's our pathlines mini lecture done. Please do like and subscribe. I've got plenty more to come.